We can't see the screen.
Okay. Hello and welcome back to Calculus 2. This is section 7.1. We are starting chapter 7 for exponential logarithmic functions. In the previous edition of this textbook, in case that you have the blue one, this is still in chapter 6. So this would be section, I believe, 6.8 in the blue edition if you have that one. So the next three sections are all on exponential logarithmic functions, and we first start by just the first lecture here to review a little bit of integration and derivatives for these particular ones. So now let's go start with exponential function first, because that one is easier and more common than logs. But logs are very important and used a lot as well. So we start with exponential function, and the first order of business, guys, is that you remember that the derivative of e to the x is e to the x. So this is the first formula you have seen, and one that you remember. Now you might have also remembered that the derivative of e to the ax, so if you have like a e to the 3x, e to the 6x or something, is a e to the ax. So this a drops down, and we show that later on using the chain rule formula that we developed in Calc 1. And then using the chain rule formula, the pinnacle of Calc 1, right, was the derivative of e raised to some f of x function. Right? So that one was e to the f of x times f prime of x. So this over here, and I'm going to box this one, is equation that you are going to use 99% of the time in your life. If you are doing calculus, you're doing derivatives of e's, 99% of stuff you ever see is going to fall in there, right? But there is a boss equation. See, e is a single number, right? The constant. 2.718281840964590, so on. So that value, right, is a particular constant. It's a particular number. But how about if I have 2 instead of that, or 10, right? So the boss equation is going to be the general case, right? The general case is going to be the derivative of any base b raised to any function f. So this one gives you the most freedom. However, it's not used a lot because the nature works with e or 10. Well, that's going to work for 10, obviously, right? So the derivative of any base, so you can have, with this one, we'll do the example immediately, you can have like 2 raised to the sine x, right? So you can do that with this formula. And the derivative is b raised to the f of x times f prime of x times ln of the base b. So I'm going to put this one on this cloud, right? Because it is the boss equation. But what I am asking you to know at all times for Calc 1, 2, 3, and DFQ is the red one. That's the one that you are going to use all the time. The one over there in the bottom is cool, but not used as much. So when do you get to experience the formula here? Well, if the question says find the derivative of 2 to the sine x, as I mentioned, right? Well, you just follow the formula. As you can see, it has first to copy the problem as is, then take the derivative of the exponent, which will be cosine x, and then multiply this by ln2. There you go. Very simple. You just follow the formula, and you get the problem. Now, most of the time, you will be using e raised to something. And let's go with e raised to the x squared plus 6. So that's going to be e x squared plus 6 times 2x, because that's your derivative there. Great. Now we're going to go and peek into integrals for e. So integral of e to the x dx is e to the x plus c. Integral of e to the ax dx is e to the ax over a plus c. Again, all of this in Calc 1. It's all 4.9. And here is the finally f prime of x e to the f of x dx is equal to e to the f of x plus c. And this one, you know, this one is hidden as the u sub actually, because your u would be f of x and then du is f prime dx. So these are the integrals. We don't have to worry about the b one. These are the integrals for ease, and all of these were studied in Calculus 1. So an example of this problem would be integral of e to the 3x dx, and you just quickly answer e to the 3x over 3 plus c, and if you have those limits, you go compute top minus bottom. You might run into a problem that has a u sub in it. So let's say you have integral of x e to the x squared dx. That would be the third case over there. You would say u equals x squared, du equals 2x dx. Now you see you need a 2, so you can fix that by placing 1/2 and a 2. And you have 1/2 integral of e to the u du, which is 1/2 e to the u plus c, which is 1/2 e to the x squared plus c. So 100% of integration that we work out in this section is going to be exactly what you learned in Calc 1. We don't have any additional stuff. And that concludes exponentials. So out of all exponential formulas that we've seen here, and we've seen like 7 or 8, only one formula is new. Everything else was a review from Calc 1, and you had a whole bunch of homework and stuff to do. Now, obviously, if you don't remember these formulas from Calc 1, you can do extra problems in this section to review those, and you are always welcome to ask questions and obviously check. The second part of this lecture is to review logs and learn, again, 1 or 2 formulas, which would be new for Calc 2. Otherwise, why have the section? If you're not going to learn anything new, why have the section? All right, so here we go, logs. So, what?
Section's over, that's it.
Yeah, that's it. So, we start with the derivative of ln x, which you all know is 1 over x, exactly. Very good. That's it. And this one you see rarely, right? You rarely see this one because 99.9999% of cases will have ln of some function. ln of f of x. I can put that in parentheses if it's going to make it better for you. So the function x now, the function f of x is not just x. Could be anything. Could be sine, could be whatever other thing. And guys, the derivative for this is so easy. You copy the function as is in denominator and put its derivative on top. I'm going to put the red box around this one because this is the formula that you use 99.999% of the time. ln of x also works there because once you copy x in the bottom, derivative of x is 1 on top. See? It's the same as the top formula. Ln of cosine, let's say, ln of cosine would be negative tangent because you put the cosine down there. The derivative of cosine is negative sine. Negative sine divided by cosine is negative tangent. So you can do a whole bunch of problems with this. And then we understand from pre-calculus that ln x is log base e of x. So ln is just a special lazy notation for us. So we don't have to spell out log base e, right? It's literally 2 letters shorter for us to write ln x, right? It's literally that. It's just a different notation for the same thing. So now you see that everything ln in our life is base e. So now we're looking for that Calc2 upgrade on this derivative where we are going to involve any base b. And that's where we get the derivative of log of any base b of any function f of x. So this is the same way we dealt with the exponential earlier, replacing e with b. So now we're again replacing that. So now the derivative over here is going to be the same f prime over f, and now you're going to have the ln b in denominator in addition, and I'm going to put the cloud over here because this is the boss equation, the general form. However, 99% of the time you're using the red one because pretty much all the time you just see ln functions everywhere. So say you have the derivative of log base 3 of, let's say, sine x. Let's say this is you're trying to make it terrible. Well, the derivative is take the function as is and put in denominator, and that's your sine x. It's always Control C, Control V for that part. And derivative of sine is cosine that goes up there because you see that it's f prime on top. And then you still have the ln3 for the bottom because the base is not e, its base is 3, and if you change the base, you have to have this ln floating around. And now cosine over sine is cotangent, so this is cotangent x divided by ln3 when you simplify it. So it goes very structured, right? As an example of the formula. Now, as I said, most of the time you will be focusing on ln formulas. So most of the time you're going to see the derivative of some kind of ln of some kind of function. So let's say you have over here ln of x cubed minus x plus 9. To find that derivative, you copy the function as is in denominator, and you put its derivative on top. Nice one. And you put the derivative on top, and you're done. So Control C, Control V, right, to copy the function on the denominator, and just look at it, and one by one take the derivative on top. Now integration. See, there is the integral for 1 over x dx, which we know it's ln of absolute x plus c. And this is something that I, in the last minute of a class, have to explain. This absolute value is not optional. You must have it. You must have the absolute value Again, this is 4.9 integral from Calc 1. So nothing new here. I'm just making sure that you remember that the absolute value must be there. And the reason why it must be there is the domain and the numbers you are allowed to plug in on the left and plug in on the right. You see, 1 over x function has the domain on both sides and not on 0. And ln x function, without absolute value, has it only on one side. So if you don't put the absolute values here, then it means that you can put -2 on the left side of the equation, but you are not allowed to put 2 on the right side of the equation because the domains, there's no domain for ln without absolute value. ln absolute x will have 2 of these like that. So you see that ln still doesn't work at 0. That's okay. The left-hand side, 1 over x, didn't work at 0. So they match the domain. This is the reason why absolute values are not optional. You have to have it. Now, in chapter 8, we are going to use a particular integral a lot, and that is the u sub with this thing. So you will have to integrate things like 3 over x plus 4 dx. These types of integrals you are supposed to know from 5.5, Calc 1 integration by u substitution. You start these problems by kicking the constant outside, and then you say u equals x plus 4. Oh, I do that. Should do that blue. Oh, come on. U equals x plus 4, du equals dx. When you plug everything in, you get 3 integral 1 over u du. And you know that that's 3 ln absolute u plus c, which is 3 ln of x plus 4 in absolute values plus c. Absolute values are not optional. Now, I really need you to start this problem, and when it pops up in chapter 8, you will immediately recognize it will be a lot. And this particular one is going to leak into differential equations as well. So make sure that what you see here is 100% understood, and ask a lot of questions if you are struggling with this stuff. The last thing that I'm going to say, if you are wondering what's happening with integral of this, well, chapter 8. So you have to wait. You do not integrate ln x yet. You will. You will integrate next week. We're going to integrate this. It's not a problem, right? It's not a taboo, it's not difficult, it's not nothing, it's just that we did not learn the technique yet. ln x is not a basic integral. 1 over x is a basic integral because it gives us ln. But ln x is not a basic integral, and just like integral of tangent, right? To integrate tangent, you have to use u sub. You write tangent as sine over cosine, and then you have the cosine to be, right, your u, and you use u sub to integrate tangent. Yeah, tangent is basic function, but integral of tangent is not a basic integral. It uses u sub. So ln x will use one of the methods we are going to learn in chapter 8. So we are not there yet, and you will have to wait for that stuff. So it's not a part of this lecture at all. But just in case you have a question, hey, how about integral of ln, because we did the derivative of ln. So that's the one that we are going to cover next week. Great. Your lab is up already. I placed it when we were talking during the break. So the lab 1, and I believe it covers all the way to revolution, I believe. It covers lab 1. So I'll post more stuff eventually. Please work as much as you can of that lab on your own, and bring your work next class. I believe there are 12 questions on the entire lab. Do as many as you can and bring them next class. So you have area between two curves, disk, shell, washer, and length of curve. If you run into any integral that you don't know how to integrate, remember, it's a lab. You are supposed to use technology. So it's there for a purpose. No one is trying to trick you or make your life miserable. You just, okay, I can't integrate this. It's not U sub. Perfect. Boom. Computer immediately, and let the software integrate for you. It's a lab. Okay? See you all next week.